Welcome back, team. We're looking at 11.5. I'm going to do a couple of videos on this, maybe 2 or 3, maybe 4. And we're looking at polar form and exponential form. So I'm going to start off by talking about polar form. You're familiar with our complex number z being expressed in Cartesian form, which is where we give an x, a real coordinate, and then a imaginary coordinate, iy, right? Okay, that's Cartesian form. We're going to look at polar form, which gives is expressed with r, theta. Now let me explain how this works. Here I have a Cartesian form of 3 plus 2i. Z equals 3 plus 2i. So if you imagine, I could actually draw a line from the origin to that point like so. Now, in polar form, we are giving r this length here. We call it the modulus. That's why we've got modulus argument form. So this is the modulus. Okay, how do we find that? Well, given that we know that this is 3 across and this is 2 up, and we've got a right-angled triangle, we know that the modulus, or the r, is equal to the square root of 3 squared plus 2 squared, which in this case we've got 9 and 4, which is 13. So r is the square root 13. Okay, well what about this theta business? Well, theta is this business here. This is theta. Well, we can find this by using tan. We have an opposite and an adjacent. So theta is equal to the inverse tan of opposite 2 over 3. And if we chuck this, I think we want to be in radians for this. So the inverse tan of 2 over 3 is 0.588 to 3 significant figures. Okay, so we could give this in polar form, or modulus argument form, so modulus, and then the argument is the angle. We would give it as square root 13, comma, 0.588. And this represent the same complex number. There's one other thing that we can say about all of this. We can say that x plus iy is equal to r bracket cosine theta plus I sine theta. You might be wondering, how the heck does that work? Well, okay. R is here. This is this length here. Cosine theta is adjacent over hypotenuse. So, cosine theta equals adjacent, which is 3, over hypotenuse, which is r. You can rearrange that, and r cosine theta would therefore be equal to 3, which is precisely what x is. So r cosine theta is x, and using the same logic, we could do the same for I sine theta. Sine theta, we know, is opposite over hypotenuse, so is 2 over r, and so r sine theta is equal to 2, and given that this form is 2, and it's on the imaginary axis, so we say it's 2i, that should be 2 up there, I just noticed that was wrong. So iy, in this case 2i, is equal to r sine theta I. Okay, so that's another way of expressing it. So we can convert between polar form and Cartesian form and polar form using this information here. So let's try a few examples of this. Question 1, we've got to convert these, which are in Cartesian form, and we're trying to convert them to modulus argument form, or polar form as we also call it. So let's have a look at this one here. If I just do a quick sketch of it, if this is my imaginary axis and this is my real axis, and I've got 1, I've got a point here. Now, I hope we don't need to do any fancy work to realise that in modulus argument form, we're going to write this as the modulus is 1, and the argument is 0. It's 0 degrees. So when we're measuring these angles, we're either measuring this way, and that gives us a positive value, or we're measuring this way, and that gives us a negative value. So the maximum value you can have is pi when you get over to here, and the least value you can have is minus pi when you come around that way. So that's a nice easy one. Let's try this one over here. 1 minus I. So if I just quickly sketch this, I'm going across 1 on my real axis and down 1 on my imaginary axis, so I'm going to be out here. And so, I'll just make it a bit bigger so you can see. Alright, so first step, modulus, I'm just going to call it mod here, is equal to the square root of coefficient here, 1 squared, coefficient here, plus minus 1, all squared. And you can easily see 1 plus 1 is 2, so it should be square root 2. What about the argument? Well, we want this angle here. So arg equals, then we're going to go tan. We've got our opposite, which is a minus 1, and over our adjacent, which is 1. And when we chuck that in to our calculator, we're going to get negative pi over 4. Just check that, pretty sure that's right. Negative pi over 4. Perfect. So that's that one done. Let's try one more over here. So let's quickly sketch it. We've gone across square root 13 and down minus 6, so we're out here somewhere. Square root 13 across, down minus 6. Let's do the modulus. Modulus is equal to square root of square root 13 all squared plus minus 6 all squared. 36 and 13 is 49, so square root 49 is 7. Argument. Now we know that tan theta, this is theta here, tan theta equals this opposite over, opposite, which is minus 6 over adjacent. So argument is the inverse tan, and I think I neglected to say inverse tan before. So inverse tan of opposite, which is minus 6, this is the down part, over square root 13. Now let's just chuck that on the calculator. Inverse tan, minus 6 all over square root 13. This is giving me equals negative 1.03 to 3 significant figures there. So modulus is 7, argument is minus 1.03. Alright, so let's move on to question 2. We're given that z is equal to half plus half square root 3i, and they want us to find the modulus and the argument in each case. So for z, okay, z. Okay, so the modulus for z is going to be the square root of 1/2 squared plus, big bracket, 1/2 square root 3 all squared. Now, when you do that, when I did it, I got 1. This is a quarter. That's 3 times a quarter, which is 3/4, so it adds up to square root 1. So the modulus is 1. Hope that makes sense. And then the argument is going to be the inverse tan of, now, if you want to quickly sketch this, we've gone across half and up a half times square root 3. So this is a half, this is the angle we want, and this is 1/2 square root 3. So we're going to go opposite, which is 1/2 square root 3 all over 1/2. And obviously you can see that's cancelling out there. So you chuck that in your calculator, and for me, when I did that, inverse tan, I get 1/3 pi, which I should remember, shouldn't I really? Pi over 3. So that is the first one. Now B is Z star. In other words, it's this 1/2 minus 1/2 square root 3i. Now, if I were to use the same diagram as I've just used here, it would be like this, wouldn't it? Remember what we learned in the previous exercise? So, you should be able to see that your modulus is going to be exactly the same. So modulus is 1, and you can chuck these numbers in there and do it if you want, but it's exactly the same. And you should be able to see also that your argument is going to be, if this is a positive pi over 3, remember we go from 0 to pi that way, we go from 0 to minus pi this way, so this must be negative pi over 3. I could chuck all of my values in the calculator and do that, but I don't really see any point in wasting my time. Okay, well let's move on. Let's do part C of this question. C. I need to find the modulus and argument of z squared. At this point, I'd like to introduce you to another form and a few rules. Exponential form, which we've got up here, is written like this, with your modulus, r, times e to the power of I times theta. So that is exponential form. And exponential form is great because it helps us be able to multiply two complex numbers more easily. Now there is some explanation for you on page 261 of how you can multiply complex numbers together, and it shows you how they come up with a rule. But I'm just going to give you the rule, and I'm going to expect you to read that proof yourself. The only thing I would say on the page is towards the end there, you might wonder how they get from the second to last step to the last step, and that's because they're using addition formulae from earlier in the book. So you might want to review your addition formula to see how they go from the second to last line to the last line. But the rules that we can use are as follows. If we've got z1 and we're multiplying it by z2, two different complex numbers, what we end up getting is r1, r2, in other words, the real values multiplied, and then the angles, the arguments, are added. Okay, so that's an important rule that we're going to use, and the reason I'm introducing it now is it's going to help us with, it's going to save us a lot of time when we start doing some of this work. The second one is if I've got z1 divided by z2, you're going to have r1 over r2, so the real parts divided by each other, and then you'll have the first angle and then subtract the second angle from it. The final one is a special rule related to this, z to the power of n, it's really related to this one here I guess in a way, is going to be r to the power of n, comma, and then n times theta. Okay, so those are a few rules that we can use. Now the reason I've introduced it now is rather than doing what we did earlier in the chapter of putting this into brackets and trying to multiply it out, which is rather painful, right? I could go 1/2 plus 1/2 square root 3i, and then 1/2 plus 1/2 square root 3i. Okay, boring, long, slow. I can now use this rule here. Okay, so if, this one here, sorry. So if I'm squaring it, I'm going to have r, whatever my modulus was. Now I worked out in question 2a that my modulus was 1 for z, so I'm going to go z2, I'm going to have 1 squared. And I also know that my argument in z, because I worked that out in question A, was, I think, pi over 3. So I'm going to have 2 times pi over 3, and so I'll have 1, comma, 2 pi over 3. That's my modulus. That is my argument. That saved a lot of time, didn't it? Okay. Let's move on to D. So with D, we're trying to do Z star, and then I think we want to square that. Now, if you look back, I think we did Z star before, and we found a modulus and argument for it. If you go back to B, for Z star, we had the modulus was 1, and the argument was minus pi over 3. Okay, so that was what Z was. Now we're going to use this rule here again. Z star to the power of 2. So we take our modulus, and we put that to the power of 2. Then we multiply by n to this. And so we have 1 comma negative 2 pi over 3. And that is the modulus, and that is the argument. Okie dokie. Now, I think the next one, E, is very similar. E is Z squared star. Okay, well, if we went back to the previous one, which was Z squared, I think we did this earlier, we know that Z squared, we had a modulus of 1, and 2 pi over 3 was our argument. Now if we're going to do the conjugate of this, this is simply going to become negative, right? Z squared is is 1 and 2 pi over 3. So what's 2 pi over 3? I don't know. Where's 2 pi over 3? It's probably up this way somewhere, isn't it? Right? Okay, so up there. Well, the complex conjugate is just reflected this way. So it'll be a length of 1 again, but the angle, instead of being 2 pi over 3, will be minus 2 pi over 3. So I would give Z squared star, and I'll just put a minus there. That's that one. Okay, well, let's move on. What have we got next? We have got G and H, I. I'll just do one more, I think. We've got Z to the power of 6. Okay, we're going to use this rule here. We know that Z was 1 comma pi over 3, as I remember. Okay? Well, Z to the power of 6, therefore, is going to be 1 to the power of 6 and comma 6 times pi over 3. What does this give us? We get 1 comma 2 pi. However, thinking carefully, remember what we said before? We measure this way, and if the angle is 2 pi, we've gone all the way around and we're back to here, which is 0, so we should write this as 1 comma 0. It can't be 2 pi. Remember, the most you can go is this way, you give the angle this way, and that's pi over here, or if you come around this way, it's negative pi. So if we've gone round 2 pi, we're back at 0 again. just be careful with those ones.